So we're talking about end of arm tooling. So we have things like vacuum devices, magnetic devices, and flexible pneumatic devices. The biggest thing with any end of arm tool is that you have to design it to meet the needs of the job you're doing. So if it's a pick and place robot, but you're having to pick up, let's say, a pool heater, you're not going to want a gripper on that or a suction cup on that. You're going to want forks. Create a forklift maneuver with it. So the vacuum device uses a vacuum cup, perforated surface, or other device using atmospheric pressure to hold and manipulate parts, which if you don't know, atmospheric pressure is 14.7 psi. Magnetics uses either electromagnets or permanent magnets to lift ferrous metals. And then you have fingers, mandrels, pin lifters that can expand with compressed air or collapse with that same principle. So this is actually what an end of arm tooling is. It's the device that attaches to the robot. It's essentially what does the job. The function or purpose is to do the job the robot was designed and programmed to perform. So literally the imagination is the limit of this, because you can make anything to do any job. They also make it to where some of the heads are interchangeable. And they can actually make heads that are automatically changeable. There's a lot of those out there these days. Kind of cool. So tooling must be able to hold and release the part or parts involved in the operation. Optional, you could make it to where it's able to respond to a signal when a part is presented, using sensors in the tool itself or elsewhere in that work cell. This is actually a very common thing because it helps to trigger the robot to actually do the job. It's becoming a very popular thing to do. It has to be lightweight. Why? Because a robot has a very specific ability to lift. So let's say you're trying to go to the hardware store and buy a bunch of things. You yourself are able to lift about 50 pounds in one hand. If you're needing to put a bag together with all these tools that equal no more than 50 pounds, what do you want that bag to be? Able to hold 50 pounds, but light enough that it adds almost no extra weight to what you're picking up, if that makes sense. Containment of the, go ahead. Exactly. So most of the time, whenever you're dealing with having to lift with anything, a lot of these are made with aluminum as one of their base components to hold everything together, simply because it's lighter than steel. It'll hold up almost as well as steel if you design it correctly and brace it correctly, but it's like less than half the weight. So containment of the part in the gripper or tool must be guaranteed under the conditions of maximum speed or the loss of power. So in other words, if this is attached to something like an overhead robot or an overhead crane, you do not want to lose power or have it lose grip and drop something on somebody. Not that you should be standing under one of those to begin with, but you don't want to damage equipment or people. You could end up with a visit promotion, definitely. So the tooling design should be the simplest that meets the 4 previous requirements. The biggest thing you can ever do with anything you're trying to engineer is find a way to make sure it stays simple. Because the more complicated it gets, the harder it is to fix down the road, and the more maintenance you're going to have to do on it. So some of the terms we have for this are end of arm tools, end effectors. One of the most common things people tend to call the end of the robot is a gripper, but that's not always true. A gripper is a type of end of arm tool. It is not the end of arm tool. That makes sense. You can have just about anything you want at the end of this. It does not have to be something that's going to come down and pick something up. Okay? So power sources, we have pneumatics. It's one of the top of the list. Why? Because it is clean. We don't have to try and return it to where it came from. It can be a very simple technology. Those are just the top 3 reasons I can think of off the top of my head. Um, Pneumatics is typically cheaper than hydraulic, if nothing else than because of the fluid that hydraulics has to be used with. Not to mention pneumatics is probably one of the most common power sources outside of electricity for every factory in the world. And again, I'm saying it's one of the most common, not the most common of all, but... Huh? It's a lot safer than hydraulics for sure. It's readily available. I don't know of many factories in the world that don't have some form of pneumatic power somewhere. It's a very popular thing to use, and it's a very common thing to use. Air is in abundance. All these things do is they pull in air from the surroundings, compress it, use it. Which is why pneumatics tops the list, because it's a clean energy, it's a readily available one, and you don't have to, it tends to be a very simple technology. You don't have to take everything apart to get to something to clean it. Spring power, the only bad thing about springs, if you've ever owned a Slinky, you know what I'm talking about. It wear out and they lose shape. So springs are something that are used, but they're generally used with something else. Actually, a lot of them are made out of carbon steel if they're going to be industrial use. Um, just because that's a very high wear item. Um, but again, springs are not generally the most favorable thing to use unless you're using it with something else. Simply because they can deform and they can wear out a lot quicker than most other forms of energy. Kind of like the springs in your car or the springs in a couch. Huh? The springs for your suspension, what goes with your um, yeah, your suspension coils. I can't remember the exact name of them, but yes, those eventually do wear out. That's why you have to replace them whenever you're sometimes working on your struts. Um, Hydraulic is used where you need a power advantage. Hydraulics is great for small actuators with large payout. However, hydraulics has its downside. One is that you have to make sure that everything goes back to the tank after it's been used. Another one is that with hydraulics, you end up with the cost of the oil, and it can also be quite nasty and messy. You have to be a lot more careful with hydraulics. You just got to have a lot more care when using hydraulics. And then one of the most common power sources in the world is, of course, electric. I don't know of almost any manufacturing place that does not have some form of electricity, if only to have lights overhead. So, groups of end-of-arm tools, we have standard grippers, vacuum devices, magnetic devices, flexible pneumatic devices, special purpose tools. Again, the categories, these are just some basic groups and categories. The list of it goes on and on because it all again depends on what kind of job you need this thing to do and how you want it to do it. This is just a quick look at some end-of-arm tooling chart. All the different ways that these guys can work. You should be able to have that in your book as figure 6.1 if you want to take a closer look at it. So standard grippers use parallel motion or angular motion. So parallel means your typical what you think of a gripper is it pops open on both sides and pops closed. Angular moves like a pair of scissor blades. So again, are very common. And we can design them to grasp from the inside or the outside. A couple different ways you can power it as well. So you have angular, which again looks like a pair of scissors, and you have parallel, which is what you typically think of as a gripper. Internal versus external gripping. So internal gripping is basically you come down and you spread it open so that you can lift up. The pressure on the piece is on the inside of diameter of whatever you're dealing with. Versus if you're coming down and picking something up on the outside, that's going to close the gripper in, and the pressure is on the outside of the object. Now, why would you want to go inside instead of outside like we would typically do? It has to do with how fragile the outside might be. So think of something like a CD. The inner ring is stronger than the outer ring. So picking it up from the inside versus the outside is a better idea. Yes, it is. Data is always stored on the outer ring of the DVD, on the CD, DVD, whatever you want to call it. So these are a pair of inside grippers. So the closed position, he's all pulled together. In the open position, he pushes itself out against it. You got another one right here that's doing similar. This is again kind of what you think of whenever you think of a gripper, is two or more clamps that are kind of come down and grab around it. Sort of like the claw machine at the arcade. It's typically what we think of as almost like a gripper, something like that that comes down and is grabbing hold of something. Servo versus non-servo, you're mostly going to run into open loop tools. Why? Because it's cheaper and it's easier to maintain, as well as most products, you're not overly worried about the death grip this thing needs to have. You're worried about cost and how well it will work, and how well, if it breaks, how can you fix it. Now, occasionally you do have some that have the ability to vary their pressure using pressure sensors, but most tooling's open loop. We don't need that extra sensor. You want something to tell you that it's there, but you don't need to moderate the grip on it for most things. So then we come to vacuum devices. These use atmospheric pressure 14.7 at PSI at sea level. So that is, if you're by the ocean, you have 14.7 pounds per square inch holding you to the ground. You have the vacuum cup. In order to use that, your surface of your object must be nearly flat, or your vacuum cup device should fit the contours of whatever you're trying to pick up. One of the coolest things I've ever seen done with a vacuum cup or vacuum surface was where Mythbusters actually lifted a car with 3 boxy looking vacuum cups that were sealed with silicone gaskets, and they used a shop vac to lift the car into the air. One of the coolest experiments I've ever seen using vacuum devices. For a vacuum surface, the entire surface is covered with vacuum holes. This helps it come down, but again, you're going to have to deal with a mostly flat surface. Okay. So you also have to know what kind of give you'll have when you're picking up this part. If something has a lot of give, let's say you have a stack of paper, how much give does this have whenever you're coming down to pick up one of those sheets of paper to move it into production? That's compliance. Okay. So you have a vacuum cup application, you have a stack of labels right here. So when this comes down, this needs to be flat, but what's something bigger that it needs to be? That's one of the main importance that is important for a vacuum cup to work. The amount of suction is a good one, but there's something bigger. I'm thinking more cleanliness. Huh? If you have too much dirt and debris on top of what you're trying to pick up with this suction cup, your suction ability will not work quite as well. So you need to have a very clean environment using one of these. Otherwise, you might suck up something unintended. And of course, this is a vacuum surface. Again, you're going to have to worry about excessive dust and such. Magnetics, you have electromagnets and permanent magnets. If I was to say which one would be more useful, it'd be the electromagnet, because you have the ability to turn it on and off at will, or to switch polarities at will, versus a permanent magnet, which you're going to have something that pushes it off that magnet so that the part can move off it whenever it gets to the next stage of production. Does that make sense? Flexible pneumatic devices, these again come in many shapes, sizes, and forms. This is a pneumatic finger application. You can't really see it that well, but this is the finger itself right here, and it's wrapping around the part. This is another very common one, especially for palletizing. So what you have here is this guy basically is a gripper that is able to push itself open and close around a bag of dog food. You got to be really careful with those because the bags tear very easily. So in transporting, setting it down, you got to be aware of where the gripper is at all times. Okay. So again, this is a very common configuration, is using them to just move things from one place to another. Alright. Just some interesting pictures here of different grippers. If you ever start looking at different grippers, they are as varied as anything else in the world. This one is using its gripper to pick up from the inside. It's expanded into the tube to hold it so it can move it onto the spool. Excuse me. You got this guy moving pieces from one place to another. It looks like it might be using suction. You got this guy right here, and you got this one right here. And this one is actually a gripper again. You can see the arms, basically the metal fingers that they've got right here. They're going to pop open and close while it's trying to grab this item. This one is a gripper again. It's coming down and clamping onto the barrel under the rim so that it actually gets a very firm hold. And you can look up, again, look up grippers and you will find that they come in all sorts of different ways. This one's a mandrel lifting device versus a pin lifting device. So this one, it uses air when it comes down into where it's picking up. It expands to fit the space and is able to use that to lift. This guy comes down and expands around the part on the outside and make it able to lift. All right. Just some different examples of robots and how they're used. All right. All right. And why is this not playing? All right, so this is a robot with an arc welding tool. Welding is probably one of the most common applications for robots other than pick and place. Again, just some more grippers and multiple end effectors. So that is end of arm tools. Anybody got any questions?